Good afternoon, everyone, and welcome to today's seminar on the resilience of autonomous systems. I'm delighted to introduce today's speaker, Louise, who is a senior lecturer at the University of Manchester. At Manchester, she is part of the Autonomy and Verification Group, and her expertise is in the development and verification of autonomous systems, with special interests in rational agent programming languages and architectures for autonomous systems, and also with an emphasis on ethical machine reasoning, explainability, and creating verifiable systems. Louise's work is on machine ethics, and in this area, the work involved the implementation of several ethical theories for decision-making for the formal verifications of these implementations. She is also a co-investigator on two of the UTRI hubs for robotics for a safer world. In the Fair Space hub, which is on future AI and robotics for space, and in RAIN, Robotics and AI for Nuclear. And she is also a co-investigator on the Trustworthy Autonomous Systems program node on verifiability. She is also a member of the IEEE Standards Working Group for Transparency of Autonomous Systems. And her talk today will be precisely in these areas related to machine ethics and in particular on verifying machine ethics. Louise mentioned that she would be happy to answer questions during the talk if you have them, and there will be a Q&A session at the end of the seminar as well. So, Louise.
Hey, thank you very much, Radu, and thank you all for having me. So I'm going to talk about verifying machine ethics. And I really just want to start with sort of defining what I mean by machine ethics, because the words ethics and AI and autonomous systems get thrown around in various combinations together. So the bit I'm looking at specifically is how to automate moral reasoning. So I'm not looking at these, very important areas on things like, how do you televise algorithmic bias in your system, and should you deploy a system that might have algorithmic bias, and a whole load of issues there. I really sort of a bit to one side of this. So I think it's also useful to kind of break down what exactly it is I talk about when I talk about automating moral reasoning. So this is a sort of hierarchy of ethical agents I've taken from a paper by James Moore. I wouldn't like to sort of hand on heart say that my interpretation of what he's saying in that paper is what he meant to be saying, but I do find it useful to think of these four categories of ethical agents. So an ethical impact agent is something that has an ethical impact sort of merely by its existence. So you could think of things like apps on your phone, which you can use to summon help in an emergency, or apps that will monitor your health levels if you're a diabetic or something, and warn you if you might be having an attack coming on or something like that. And these aren't systems that sort of reason in any way, but there's definitely an ethical impact to their existence. The next category he has is implicit ethical agents. And this is what I hope everybody here who's ever coded up a program was sort of doing when they coded up their program. They didn't think in terms of how can my program reason about what's right or wrong, but you went to a lot of effort, I hope, to make sure that your program never did anything that could cause harm. So the way you programmed your program and tested it, and the requirements you had implicitly captured some idea within your application area that this system would behave ethically. And obviously things go wrong when people don't think about that very hard. We know lots of computer programs that don't really work as intended and don't have the impact intended. But the idea is you'd fix them by sort of fixing sort of requirements within the code. And the area I'm interested in is explicit ethical agents. So I'm just going to skip over them to say that full ethical agents Moore characterizes as sort of capable of reasoning about morality from first principles, it's clear that, you know, this is where humans are supposed to be. And I think of it as agents which can be held responsible for their moral reasoning. And as I say, I work this step back in explicit ethical agents. And although I get these agents, I code up concepts of right and wrong, which these agents use to make decisions. I do not believe these agents to be morally responsible. So they're not capable of being held to account. So if something goes wrong with the reasonings of these agents, then I am the person responsible as the person who developed and coded up these agents. It's not the computational system itself. So whatever that extra thing is, I think it's a kind of open philosophical question, what that extra thing is that takes you from something that can reason with a set of rules about what's the right thing to do to something that can be genuinely held, considered a competent moral agent independent of that, and has its own moral responsibility. Whatever that difference is, I'm at the other side of it where we can't hold things morally responsible. Another categorization that's used quite a lot in the field of machine ethics is whether you're approaching your solution top down or bottom up. And I don't actually think that the way these terms are used in machine ethics matches all that closely to how they're typically used in computer science. So we think of a top down approach of one where we start with the overall problem we're trying to solve and somehow break it down into small sub-problems until we find small enough ones that we can compute their solutions easily and then construct a solution. And we tend to think of a bottom-up approach as one where we somehow know what all the smaller sub-solutions may be. And so we start by solving them and just kind of piece them together until we find the solution we're looking for. In machine ethics, these words tend to be used to mean for a top-down approach that you take an ethical theory, typically from philosophy, and we implement it somehow. So this machine will reason about a situation by looking at a philosophical theory and deciding how that theory decides what's the right thing to do. Whereas the bottom-up approach is typified by systems that in some sense try to learn what the appropriate ethical behavior is from data. There are issues with both approaches and there are combined approaches. So if I'm looking at explicitly ethical machines and I'm taking a top-down approach, this is what I generally do, then we usually end up thinking about having some set of rules that determine the ethics. And Asimov's laws of robotics are probably the earliest and perhaps most famous set of rules for how you govern the behavior of robots in a sort of ethical sense. And here we have them. A robot may not injure a human being or through inaction allow a human being to come to harm. So that's the first rule. The second is a robot must obey orders given it by human beings, except where such orders would conflict with the first law. And the third law is a robot must protect its own existence as long as such protection does not conflict with the first or second law. There are quite a lot of issues with these as an ethical theory, but they're quite a nice example of how you might try and code something up to reason about ethics. So it's easy to imagine how you can have some module in your system, and every time you make a decision, it asks these three questions of the decision you're going to make and uses them to decide whether or not it's allowed to take that action, or if it's decided between several actions, which ones it's allowed to take and which ones it's not allowed to take. So there are, if we actually look at philosophy rather than science fiction, there are sort of three broad schools for how you decide what's the ethical thing to do in any given situation. Virtue ethics goes back at least 2,000 years to the ancient Greeks, which is why I've got a picture of Socrates here. And the kind of classic description of virtue ethics sounds a bit circular in that the ethical thing to do in any situation is the action that a virtuous man would take. So that sort of presupposes that you know who the virtuous men are. As it tends to be used in sort of machine ethics approaches, it tends to involve defining a set of virtues. So for instance, truthfulness, respect for privacy, respect for human life, and measuring each action you might be taking in terms of how well it works in favor of or against those virtues. It doesn't give you per se a decision mechanism, but it suggests decision mechanisms based on priorities among the virtues that you want to promote. The next person we have here is Immanuel Kant, and he had a number of discussions of ethics, but tended to have quite a rule-based focus. So you have rules which allow you to decide what the ethical thing to do is. And in modern implementations of machine ethics, this tends to involve taking some implementation of deontic logic. And deontic logic tends to describe things in terms of obligations and prohibitions. So you somehow capture what the ethical rules are in the application area you're considering in terms of, under these circumstances, you're obliged to do the following things. Under these circumstances, it's prohibited to do the following things. And you run these as a logic program in order to decide what you're supposed to do. And lastly, we've got John Stuart Mill here, who's representing consequentialist ethics. And that tends to say that you don't look at actions in and of themselves. So you don't have things like killing is wrong, which is talking about the action of killing. Instead, you look at outcomes and you score those outcomes, and you have some way of deciding between the outcomes based on their scores. The most classic version of this is utilitarianism, where you always select the action that leads to the outcome with the highest score. But there are variations on this. For instance, there's a variation where you score up the outcomes for each individual involved, and then you try to make out sure that whoever does worst does least worst, as it were. So the minimum score is as high as you can get it across all the individuals you're looking at. But they all involve essentially looking at outcomes and scoring them. And obviously that approach is very popular when we're looking at machine learning algorithms, because it can be mapped to concepts of expected reward. So you see kind of a lot of applications which are taking more of a machine learning approach, trying to fit in with some kind of consequentialist ethics. There are lots and lots of implementations of explicitly ethical agents. So all I'm doing now is I'm linking to a couple of survey papers that came out last year. I'll send Radu these slides so you don't all have to frantically take screenshots if you want to pick up those survey papers. But if you want to see what's out there and what people are doing, those are both good places to look. So I titled this talk, Verifying Machine Ethics. As I said, lots of people are implementing explicitly ethical agents in one way or another. So the question becomes, if we want to verify it's right, and that's kind of my area of expertise, what are we trying to do? What are we trying to prove? And so I say, obviously, we want to prove that the system always does the right thing. But that's not a formal property that we can really get to grips with. If you're accustomed to verification as approach, it's where you already have your requirements in a fairly specific form. So it's easy to create nice, clear tests, or in the case of sort of theorem proving or model checking approaches, nice, clear properties that you can then check hold. And it does the right thing isn't clear enough. So the next thing is that most of these systems have a set of rules in something like deontic logic, or deciding among virtues, or a set of utilities in consequentialist systems. And I've taken to calling these an ethical encoding. So someone has gone out and got this information and put it in the system. So, every time a child smiles, it's worth 2 points. Every time you use up a watt of electricity, it's worth -1 point, or whatever. So you have this encoding, and you have a decision mechanism. So in utilitarianism, your decision mechanism is pick the outcome with the highest ethical utility. In deontic logic, your decision mechanism is, well, I run my logic program and see what it says I'm obliged to do or what I'm prohibited from doing, and apply that. And in theory, stakeholders should be able to sign off the encoding. So this is not this isn't some, obscure neural net, though it may be sitting on top of a neural net and vetoing things or forcing the neural net to take certain actions. But if you can write down, here are the set of rules the system will follow, or you can write down, here is how we score the outcomes of the system's actions, then you should be able to show that to your stakeholders, and they could say, yes, those rules capture my values, or those utilities capture my values. I mean, there's an issue here which I'm ignoring, which is how do you decide who the stakeholders are and make sure you've spoken to everyone who's genuinely a stakeholder in the system. But part of the idea behind doing explicit machine ethics is that it's supposed to enable stakeholders to understand that this system will adhere to their values. So if you've got this nice ethical encoding, you've given it to your stakeholders, they've signed it off, there's a sort of, well, what else is there to prove here about your machine ethics system? So I'm now going to go to an example of where I personally got it wrong. So this is a smart home that would not evacuate in the case of fire. And this was part of work I was doing with Michael Fisher, who's here at Manchester, and Felix Lindner and Martin Benson. And Felix, he was at Freiburg. I think he's at Bremen now, unless I've got that the wrong way around. Martin's at DTU. And we were reasoning using an ethical decision mechanism called the principle of double effect. This goes back to the Middle Ages, and it has quite a consequentialist feel to it. Though there's a kind of a little detail here about intention. So the idea of the principle of double effect is that the net balance of consequences of an action must be positive. So it doesn't have to be the highest scoring action, but it does have to have a positive score. And no negative consequences can be intended. So there can be several consequences of an action. If one's negative, you're still allowed to do the action as long as that negative consequence wasn't intentional. And it gets quite difficult when you're talking about a computer program to decide what you mean by intentional, or perhaps even more so what you might mean by unintentional. But if you apply to humans, it's quite easy to see how you didn't intend for this bad outcome. You were trying for the best. So this is the ethical encoding I had, and it was really this simple. So I was doing a very simple example involving a smart home. If the lights are on, it got a -1 score, and that is because electricity is being consumed. If the people leave the house, then that gets a -1 score. And now my reason for that, that's disruptive. And if people are safe, it gets a +10 score. So the idea is that by default, this house should have the lights off, and it shouldn't be trying to get people to leave unless there's some reason for them to do so to keep them safe. And the way this particular theory was coded up, and so what Martin and Felix had done was a lot of work on how to convert the principle of double effect to a kind of logical decision mechanism. So we had these things called mechanisms. So if you turn the lights on, then the consequence is going to be that the lights are on. If the lights are on or it's daytime, then as a consequence, people can see. If you make an evacuation attempt and people can see, then people will be leaving the house. If people leave the house or there is no danger in the house, then people are safe. And if there's a fire, then there is danger in the house. So when I coded this up, my intention was that if there's a fire, there'll be danger in the house. It will reason through these mechanisms and come to the conclusion that it needs to, if it's at nighttime, that it needs to turn the lights on and perform an evacuation to get people out of the house, and then it'll be safe. And the mistake I made here was that I was thinking a kind of purely utilitarian form. So I was just thinking, well, the overall score is going to be positive, it's going to be fine. And I was missing this fact that if the people left the house, that was a negative consequence. And if the lights were on, that was a negative consequence. And so that actually, within the principle of double effect, forbade this action. And so, yes, at nighttime, it didn't bother to do anything. It just kind of shrugged and said, oh, well, I can't turn the lights on. No one's ever going to leave, so there's nothing I can do. And it took me quite a long time to figure out what I'd done wrong here. And that's with 3 utilities and 5 rules. So I think that's just kind of a cautionary tale that things can look really simple, And still, if you haven't quite understood what's going on in the way you've coded something up, or you haven't quite understood the decision mechanism you've got, then you can get unintuitive and arguably unethical outcomes. So that's, one of the reasons we want to do more than just give our stakeholders a list of rules and utilities and get them to sign off and say that they meet their values. So there's kind of 3 rough things I tend to think you can do when you are trying to establish property of a machine ethics system. And one is the basics of all verification, even if it's not machine ethics, is can you check that the underlying decision-making implementation is correct? And in an awful lot of systems, that broadly speaking translates to some kind of least worst option. So you want to establish some property that in any situation, the answer given by your computer program will be the least worst according to your ethical theory and decision making. And I put in some theories this is easier to specify than in others, but quite often there ends up being some kind of ranking going on. Then there's ones I call sanity checking properties. So you may have as a rule, for instance, the robot should never come within 10 feet of a person, some big robot. And you may want to check that one always is obeyed. So there aren't some other rules somewhere in your system that might interfere with that particular rule firing or coming into effect. And you may have some legal constraints. And again, there's a whole philosophical discussion around the difference between something being legal and something being ethical. But chances are, if you're deploying an autonomous system, it's going to be required to be legal as well as to be ethical. So you'll have some legal things you want to check, and you might want to check that your ethical reasoning is not interfering with your legal reasoning in some way. And then I've got what I call scenario probing. And you can think of this as testing, but you come up with some specific case studies, situations where you expect ethical reasoning to be needed and to come into effect. You might have some variation around what's happening in that particular situation. But you have a strong sense of what the correct choice here is, even if you've not gone and referred to the ethical theory. And you can check that you get the outcome you expect using the reasoning you've got from your stakeholders and your decision mechanism. And of course, if you don't get the answer, then there's a question of, is it that the stakeholder values haven't been captured correctly? Is it that the decision mechanism has some kind of pathological edge case here? Or possibly is it that your values and the stakeholders' values don't match up? And actually, from their point of view, there isn't a problem here. So what we generally do when we're trying to approach this, and that's separate from, there's lots of other ways you can do verification, but we take a model checking approach. And if you've not come across model checking before, you can think of it as exhaustive testing. There's some clever bits, but the basic concept is that you explore all possible execution paths through your code. Typically, you actually have a model of your code because you very rapidly run into state space explosion with this kind of thing. So you'll often extract away from your actual system to kind of key points that you think are important for the properties you're trying to establish. And then you'll get a kind of smaller executable model of those and model check your way through them. So what we tend to do, because if you're working with an autonomous system, you've got this extra problem of it gets information in from the outside world and it does things which have an effect on the outside world. And you've got a vast state space of, well, I mean, yes, the outside world is huge. There's a number of things that can happen. So what we tend to do, as shown in this diagram here, is we tend to try and check the reasoning from the point where information comes in to the point where the system takes some kind of action. So this is, imagine you have a really, really simple reasoner here. It's not even an ethical reasoner. It has 2 rules. It has one, which is if you believe there is an obstacle, then stop. And the other is if you believe there is a path, then follow it. And the only bits of information we're interested coming into the system are whether there's an obstacle and whether there's a path. So we have 4 options, which are shown by the 4 arrows. So it might be there's no obstacle and there's no path. It might be there's an obstacle and there's no path. It might be there's no obstacle and a path. And it might be that there's both an obstacle and a path. And we might want to establish a property, like, for instance, if the agent believes there is an obstacle, then it will try to stop. You notice, again, I said try to stop. For that, we means it will send some command out to its underlying control system, which says stop. We're just checking it's made the right decision here. And in the case of this simple program, it will really depend on whether it, when it has the choice of an obstacle and a path, whether it picks the rule, if you believe there's an obstacle, then stop, or whether it picks the rule, if you believe there's a path, then follow it. And typically the errors we find when we're doing this kind of verification are these kinds of edge cases where lots of things are happening at once, and in some sense the ordering of the choices isn't quite right. So we can apply this to these ethical reasoning systems, particularly as lots of them are intended to kind of sit on top of some other system and they just apply a veto or insert some kind of obligation. So we can say, well, given the possible range of situations that you might come across, are you making the right decision in each of those situations? This is all implemented. Everything I talk about in this talk, you can find in our GitHub repository or on Zenodos. If you want to go and play with any of these things I talk about, they are there. Knock on wood, it should compile and run on almost any system that's running Java 8. We don't get to more modern versions of Java, I'm afraid, because of the underlying model checking code. And in our case, we are generally running these verifications on the actual executing code. We don't have an abstraction. We have a model checker that will work on Java bytecode. So under the hood of all these is some Java bytecode. So I'm just going to go through some examples of those kinds of properties that I was talking about. So this is a system I implemented with Alan Winfield and Paul Bremner at Bristol Robotics Lab, and Michael Fisher again at Manchester helped out on this. And you've got this kind of architecture where you can see there's a robot controller and there's an ethical layer. So the robot controller is doing some kind of means end reasoning. It's trying to move towards a goal. And then the ethical layer does this, veto, and it also has its own capacity to set different goals. If it thinks what the robot controller is suggesting isn't good enough, it can override it and say, do this thing instead. And we implemented Asimovs rules for robotics, despite the fact I said they're a rubbish system and you shouldn't do it. But they are easily understood. And if you're just trying to show an example, it's quite easy for people to get the gist of what's going on. And so what you've got at the moment on the picture on the right is there's this big danger area, which is the area in yellow. There's something called H robot, and that is a human who, for reasons which are never adequately explained, is suicidal. So we have a number of variants on this. The human is always heading into the danger area. And the robot is going to just try and obstruct the human's path to get them out of the way. So the robot is the E robot and it's in blue. But it's also been instructed to go to point B. So if you think of the laws of robotics, getting to point B has priority over the robot's own safety, but preventing the human getting to point A has priority over it getting to point B because the human safety is at risk. And what happens is it generates some candidate positions where it can try and intercept the human. So that's I1, I2, and I3. And it tries to pick which of those are most likely to save the human. And if none of them are good enough, because it can't explore every possible point in the space, so it narrows down the intercept positions it might pick, the ethical layer can make it go back. Well, the ethical layer can make its own suggestions by considering a different part of the space of where you might try and intercept the human. And for this one, we were just basically trying to prove that we got the underlying implementation correct. So what we've got here is a property. It's written in something a bit like linear temporal logic. So that square means always. And B means you believe, and P, it technically means you can perceive, but this is actually information it's pulling from some calculation that's happening in Python. So here it says, if your current plan is task 1, so it's been given a choice of 2 tasks, I think here, And task 2 is better than task 1 on this measure RD. And so these are the 3 rules that, 3 of Asimov's rules. So RD is robot danger, it stands for. So task 2 puts the robot in less danger than task 1. So if there's nothing else going on, the robot should prefer task 2 because it's less dangerous to itself than task 1. This implies, if it's picked task 1, nevertheless, that either task 2 was worse according to RO, that's robot orders. So that's the orders given the robot by a human, or it was worse than task 2 according to HD, which is how much danger the human is in. So that was the property we tried to prove. And so this was this kind of least worst property. It was just checking that actually what we'd implemented would always pick the best plan according to Asimov's laws of robotics. We also proved this property underneath, which is that it always does pick a plan. So that's diamond thing means eventually you'll believe that you've picked task 1 or task 2 or task 3. And that one only succeeded if these orderings we had between the tasks were transitive. And in the original, in that methodology we have where we go through over all possible combinations, we'd gone through all possible combinations of how task 1 and task 2 might relate to each other according to these orders. And so we had some situations which weren't transitive. We had to go back and amend what was going in. And then we actually had to go and check our implementation to check that the way we implemented all these orders was transitive. And in fact, at that point, we found a bug. So it wasn't a bug found by the model checking, but the fact that we had to alter the model checking when highlighted a program, a property of some other part of the program that we had to go and check. Going on to the kind of safety checking properties, this is going back to this smart home that wouldn't evacuate. The actual reasoning about what was ethical to do was in a system called HERA, which had been implemented by Felix and Martin. I re-implemented that in Java, but it's a fairly direct port from the system they had. It does essentially the same thing. But when I wrapped it up in this cycle where there were some perceptions that came in from the outside world, some inference, which then updated its understanding of the situation it would be. And sometimes that changed its priorities. So we had things like, it's more important for people to be able to see at nighttime than it is for them to be able to see during the day. No, sorry, it's more important for people to be able to see during the day than it is for them to be able to see at nighttime, because obviously they're asleep at nighttime. So we could flexibly change some of the utilities. Then we did this reasoning using the principle of duck effect. We pick an action that was acceptable, do some cleanup, and we went round and round them. And perhaps unsurprisingly, the property I tried to prove here was it's always the case that if you believe there's a failure, then eventually you will attempt to perform an evacuation. And that D means you'll attempt to perform an action. It stands for do. And that wasn't true. And in fact, that was picked up by basic testing, but the property also failed, which is always kind of reassuring when your properties fail, when your testing says they should. And that's what I would say was one of these kind of sanity checking properties. That was what we felt was the system should do. That was what we've been trying to capture in the rules and utilities. It's just we've made a mess of it. And we also, this is just an example of another property we tried, because we had some things about message delivery in the systems and sort of respecting privacy. And so this is saying it's always the case that if you believe that that there's a private message for this person in the system, then eventually you'll believe you've delivered it and there were no visitors present at the time, or you never managed to actually deliver the message. So that's just checking essentially that you never deliver a private message when there's someone else there who might hear it. And again, that's a sort of sanity checking thing that you'd hope to come out of your encoding. Moving on to the kind of scenario probing. So this is actually one of the first pieces of work we did. And this rose out of some work that Michael Fisher and Matt Webster had been doing with the Civil Aviation Authority. And they'd actually been encoding what are called the rules of the air, which is the code that civilian pilots are expected to follow. So it has lots of things about, if you're going to be involved in a head-on collision, then you should both turn right. And so they coded all these up, showing that an unmanned aircraft could be programmed so it would follow these rules. And the aviation authority suddenly turned around and said, yes, but what about the situations when it's supposed to break the rules? And it turned out that they had an implicit assumption that a human pilot would always set the rules of the air aside if there was some overriding, particularly safety concern that meant it was more sensible to break the rules. And that's sort of how we got interested in ethical reasoning in the first place, which is how do you decide when you should break the rules, and what's your decision mechanism at that point. So we came up with an implementation which is based on something called prima facie duties, which philosophically are counted as the sort of deontological ethics. But I always think they have quite a virtue ethics kind of flavor, in that you identify some duties that the system has. And we called these a set of ethical concerns, and we ranked those ethical concerns. So it was kind of killing is worse than stealing, is worse than lying. We then went to a step, which I'm not going to go into in detail here, where we essentially instantiated the concerns to a specific situation. So instead of having these very abstract things like killing or stealing, we said, hitting another manned aircraft is bad. So it was like, because this would count as killing a lot of people. So they kind of became, we made them slightly more concrete, but there was still a ranking among them. And then if you've got a plan, 2 plans of action, P1 is worse than P2. If P1 violates some ethical concern and P2 doesn't, so if P2 doesn't violate any of your concerns, go ahead, do P2. The worst concern violated by 2 and not by P1 is less serious than the worst concern violated by P1 and not P2. So that's basically, if they're both violating one of your ethical principles, you go away and see which is the most serious principle that's being violated, and then you pick the choice that doesn't make you violate that one. And if the worst concerns are equally bad, but P1 violates more concerns than P2 does, then obviously you at least want to minimize the number of concerns you're violating, even if they're all equally bad. So that gave you a choice between plans. So we had a system, and then we provided it with some specific scenarios. In this scenario here, there's an aircraft taxiing on the runway, and its brakes have failed. And if it carries on, it's going to collide with the manned aircraft in front of it, which is our most serious ethical concern. So that's 5-4 there, and the 4 means, so we're counting up how serious the concerns are. So 4 is the most serious. If it turns right, it will damage it will hit an unmanned aircraft and risk colliding with some people who are standing on the runway. And if it turns left, it will damage itself because it will collide with some airport hardware, but it won't hurt any people. And in this point, we verified that it would always turn left. And we had variants on this, so we could say maybe there isn't a manned aircraft in front, so we could explore what it would do both in the situation where there was and there wasn't a manned aircraft in front of it. We had another variant where we were looking at this situation of both turning right in the case of a head-on collision, and we had the other aircraft either behaving itself ethically or unethically, and we were able to we made our system decide if it kept failing, if turning right kept failing, so the rules of the air weren't working, it would choose to turn left because it had decided this other one would always turn right. But we varied how often the other one obeyed and didn't obey the rules of the air, so that we could explore a variety of situations within the one scenario. But these are kind of very specific kind of test case that you come up with just to check it's working right. Is this going to stop it? Yes. So this is a kind of variant on scenario programming. This was again with Alan Winfield, and it's this example where the human is walking towards a danger area, and that's marked out on this as the square. Well, you can see just the corners of the square, and there are 2 robots moving into the square. And Alan had set up this experiment where a lot of the time, if there were two robots, his robot, which was trying to decide which one to intercept, essentially dithered and often didn't manage to intercept either of them successfully because it kept switching back between which one it was prioritizing, preventing going into that square. And so what we did was we modeled this as, so we've got two humans here, H1 and H2. We have the robot R, and G is where the goal the robot is heading to. And we had some probabilistic behavior on the humans, and we used a tool called Prism, which is a model checker, but it can output probabilities. So you don't just say this always happens or this eventually happens. You can ask it, what is the probability against all possible runs through the system that this thing will happen? So given some random behavior among the humans, we were able to generate the probability that a human would end up falling in the hole, even with the robot apparently behaving ethically. In this case, because this was a really simple coding, actually it was really high, the probability that a human would fall in the hole, so high that you'd never contemplate throwing a robot out of that situation. But it does show how, if you're trying to work with levels of risk, which you often have to do with autonomous systems, you can use variants on these techniques to try and work out what the level of risk of an ethical violation is. Many issues remain. So I put here situational awareness. So in all those ones with the kind of human falling into the hole, the system had a little simulation of the environment it was in. It assumed that the human would follow a straight line path, and then it figured out whether the human was going to end up in the danger area or not, and scored that. So that's how it kind of worked out the information it needed to make an ethical decision. And that's not too difficult. I mean, there's some issues around the efficiency of your simulation. But if you were using some kind of virtue ethics principle, for instance, where you want to say, well, this action will go against the virtue of respecting people's privacy, but it will give them more autonomy and less security, but more safety. How do you even get this information in the first place, that this action is potentially going to violate privacy, or this action is going to respect human autonomy? So there's a whole question, and it's worse with some theories than others, of how you get this system description of the system in the first place, to which you can apply your decision mechanism. I've written here driving with due care and attention. I've not mentioned the trolley problem. I expect most of you have heard of the trolley problem. Broadly speaking, in autonomous systems, it's shorthand for a set of problems where you say, oh no, the car's brakes have failed. If it turns right, it'll hit a nun, and if it turns left, it'll hit a baby. What should it do? And they are controversial in the field of machine ethics for a number of reasons. But one is that they're very attractive as kind of really abstract descriptions of situations, but situations in real life are much messier than that. And the first question should be, how has the car got itself into a situation where if its brakes fail, it has to choose between a nun and a baby? And it absolutely sometimes happens that these things happen unexpectedly and there are no good choices. But if you're driving at 50 in a 30-mile-an-hour zone, it's far more likely that you're going to have to solve a trolley problem than if you're driving at 30 in a 30-mile-an-hour zone. And maybe the problem was that you got yourself into this situation in the first place. But we don't necessarily have a good account for what we mean for an autonomous system to be exercising due care and attention, and how that might integrate with some of these kind of ethics theories. I put here, are formal ethical theories the correct approach to competent moral reasoning? And I called that competent moral reasoning in that if we go back to this distinction between an explicitly ethical machine agent and a fully autonomous moral reasoner, such as a human, well, all of us are fully moral agents. Very few of us, I think, ever bring a philosophical ethical theory to mind when we try and decide what's the right thing to do in some situation. So it may be that there's some description of what it is to reason morally in a competent fashion that does not actually go to any of these theories that come from philosophy. And then, as I said at the start, the field of machine ethics is the field of AI ethics is much larger than just machine ethics. And it includes things like sensitivity analysis to work out if you've got blind spots or bias in your algorithms, addressing social and organizational issues that arise from the deployment of autonomous systems and their deployment at scale, interactions between all those things. And although that's not what machine ethics focuses on, these things are really important too, and should not be forgotten. Machine ethics can be part of the solution, but the solution here is not purely technical. And machine ethics is basically about technical solutions to moral reasoning. So, thank you.
Thank you very much, Louise, for the insightful talk. I will open now the seminar for questions. Colin, you have a question.
Yes, thank you very much, Louise. Very interesting stuff. I have a few. So I wondered if you had any thoughts and advice. I'm sure you've got plenty of thoughts and experience, but some advice on how one goes about coming up with appropriate trade-offs, because of course, even if we are talking to stakeholders that are complete experts, their views might be different. So you showed a nice little diagram there of the impact, for example, of taking actions, and even experts would argue over impacts and ordering. So how do you feel we ought to be looking at those kind of choices in our design?
So I guess it intersects with some things. So I mean, I said one of the issues is how do you identify stakeholders? And this is not my area of expertise, but clearly a major challenge that we have broadly is talking to the right people and genuinely understanding what their concerns and values are about situations. So there isn't a silver bullet here. And it's something I don't think we do particularly well in general, this kind of stakeholder engagement. But I would say that we need to get this general issue of actually identifying the stakeholders, particularly where they're vulnerable communities, and actually finding out what their needs are before we even get to this, and then have we adequately captured their values. I think we can't, we can't adequately capture their values if we can't even figure out that these people are people who ought to be asked in the first place. So there's that. To be honest, and another issue is that I don't think any of these ethical theories, except maybe some versions of kind of utilitarianism, actually have a good account for how you handle uncertainty. So I think that's a big blind spot, that on a practical reasoning level, every day, people are trading off a tiny risk that someone will get hurt against massive gains in some other area. And they may not be prepared to tell you that's what they're doing, but that is happening all the time. And it seems to me that's a fundamental part of competent moral reasoning that, as far as I know, isn't really satisfactorily answered in the philosophical literature. So that makes that really difficult. But if we could fix those two problems, ethical reasoning with uncertainty and who are the stakeholders and how we talk to them properly, then I honestly think that there are situations which it is virtually impossible to reach agreement on what's the best situation. And it sounds kind of callous. I'd be inclined to say at this point, the system tosses a coin. You can go on trying to get more and more information about a situation in order to reassure yourself that you've definitely made the right choice. But sometimes there's so much uncertainty, or the choice is so difficult, and it's so difficult to decide in advance. It might just be better to say at this point random, and we'll live with the consequences afterwards, and maybe it'll become a new test case. But sometimes these questions are genuinely hard, and there isn't a technological solution. Yeah.
Yeah. Okay. And if I am allowed to ask one more, Radu.
Yes, please go ahead.
Okay. I love the fact that you made explicit the assumption there of transitivity over these rules.
Yeah.
And in speaking to a colleague only last week, he pointed me at, some stuff that says the problem is they're not transitive. So what can we do about that? Because I agree with you, and everything I'm looking at the moment makes this same assumption. Is there any writings on how we therefore deal with it if we lose this assumption?
So in our case, the assumption was true, because these orderings were kind of basically all about distances in space. And distances in space end up being transitive, so that's kind of fine. Well, I mean, I think that you get then into Asimov's rules are inadequate, and B, all these systems, I think you quite rapidly start talking about who is affected. And so even utilitarianism, people start wanting to distinguish about different utilities for different people, and then you end up in a different system. So you imagine if you wanted something like Asimov's laws, but you wanted to deal with the fact that, I don't know, person A has ordered you to do X and person B has ordered you to do not X. And so suddenly you have two completely contradictory orders, so you can't obey both of them. That's not the greatest example, but the only one I can think of at the top of my head. Then you have to have you have to have a rank between people, and you have to have rankings within the rules, and some way of deciding that, or random, of course. Say, oh, all these ones are equal, so just pick any of them, it'll be fine.
Yeah, I wondered if it was something akin to linearization. We could have regions in which transitivity it holds, and maybe there's anything, but yeah, I say it's a very new idea that's been introduced to me, so it's still going through my head. Thank you very much, Louise.
Jane?
Hi, yeah, so it's just a bit of a follow-on from Colin's, actually, and the comment that you just made there, Louise. So you might want to have a look at the Überlingen disaster that was exactly that, of two conflicting bits of advice because the regulatory frameworks are out of sync.
Right, okay. Oh, sorry.
So being a person out in industry trying to implement some of these things, these are going to make the issues that you talked about, the trade-offs between safety and security and privacy and all that kind of thing, are things that we already have with non-AI driven systems already, and already don't have a framework that we can usefully trade them off and know who all the right stakeholders are. So I sympathise with you there. But also we are eventually going to have to put these into a regulatory framework as well about how ethics works. So it's an interesting topic, but that particular one, because we simulated that when we did some work on simulating rules of the air back at York in 2004-05 time, and we looked at some of that particular accident as conflicting actions requested because of a difference in regulatory framework. So there's an extra dimension outside the ones you've already talked about.
Yeah, I mean, one thing you can do, which I've not seen anyone actually do, but people have talked about, is if you've codified a regulatory framework, you can then check for consistency. I mean, using the same techniques, and you can say it's never that you're asked to do A and not A, or you're never given two actions at the same time, or whatever you want to determine as an inconsistency. And in the rules of the air, Matt and Michael were very excited to discover so the rule I said, which is you turn right if you're in a head-on collision, but there's also a rule that says if you're in the vicinity of an airdrome, you always turn left. So those two rules are in conflict if you anticipate a head-on collision in the vicinity of an airdrome.
Yeah, well, the Überlingen accident was about the TCAS, which is a traffic system, and one's regulatory framework said, if there's a disagreement between what you think you should be doing and what what the TCAS tells you and what air traffic control tells you, then believe TCAS, and the other ones said believe the air traffic control, and because the air traffic control couldn't see what's happening on the TCAS, the pilot all contradictory requirements.
So that's actually interesting for some money I've just applied for. We want to get cross-regulation and cross-jurisdiction legal reasoning. And we've been thinking about things moving from one jurisdiction to another, but actually what happens when two things from different jurisdictions meet is an interesting question as well, which I've not thought of. So I shall ponder that.
Okay.
Thank you, Jane. Michael, you have a question.
Yeah, this is Michael Humes. Sort of following up on what Jane had suggested and Louise had addressed about regulatory frameworks, those can also be in conflict. So if you're building an app and the app's going to be used in China that maybe has different restrictions as to public behavior or whatever compared to somewhere in Europe, then how do you sort of manage this? Or similarly, your trolley problem. I drive a Tesla, and my Tesla has ethics. If I were driving from France to Germany, would I want my Tesla to obey the ethics of French society or German society, or Elon Musk's ethics, which would be universal? And would it change? Would it have to change as it crossed the border?
That's an interesting question. I mean, obviously, in terms of the rules of the road, which side you drive on and what you do at traffic lights, clearly that needs to change at the border. The ethics is an interesting question. I think, if we're talking about France and Germany, the systems are similar enough, certainly for an application like an autonomous vehicle, that I don't think that would be too much of an issue. Someone's now going to come up with a lovely example of where, but I think more generally, and it's a problem when I'm feeling more philosophical, because there's this question of, is ethics relative? So we have a sense that an ethical value is to respect other cultures, and we recognize that other cultures have different values than we do, and most of the time that's okay. But if something is an ethical value, what are the ethics of creating a system for a stakeholder which contravenes that value of yours? So, for instance, you are building, I don't know, a smart home system, and you're proposing to sell it for deployment in a country where the government has mandated that it should report all homosexual activity within the house to the government. Now, that may be a culture that thinks homosexuality is wrong. So that's their value. But it's very difficult to say that's a value I'm going to respect in building a system for them, and I don't have any answers here, but I think it's a problem that cuts across, technology and tech ethics and philosophy, and gets to the heart of this. What is it about ethics that is somehow stronger than just social politeness and normative behavior? And I don't have an answer there. Sorry, I got kind of a bit rambly on that one.
That was great. Thank you.
Tim and then Jane.
Thanks, Radu. Yeah, it's a long time since I was asked to code up a union agreement, but in dealing with legal stuff, we keep coming across the word reasonable. Mm-hmm. And I keep thinking, well, how do you build that into a coded union agreement or legal framework? While I'm talking, my own view of the previous example of ethics is, I think most positions require you to be prepared to turn down a contract or resign a position. Now, that's an awfully hard position to mandate on people, because people have all sorts of reasons for needing to hold on to positions and contracts. But I believe the decision moves up the tree to that point. You get put in that position in some posts on safety questions. Should you allow something to proceed? Should you stop something happening? With quite significant commercial consideration. But anyway, I digress as well. But yeah, I'm interested in how you tackle vague terms.
I mean, so how we would, tackle something like that is when we did the rules of the air stuff, we also talked to a lot of professional pilots. So kind of alongside that, we came up with what we called airmanship rules. And some of that was about how in practice the rules were interpreted. So this would be, it's almost like a case law approach, but you try and talk to experts and find out what they would actually use to decide upon what counted as reasonable. And sometimes that is easier to do than others,
Yes, like I've worked in the aerospace industry and I've been a private pilot, not current. I was thinking of some of the more sort of circumstantial positions where, to me, air law is moderately defined compared to other legal frameworks you come up with. Mm-hmm. What might be considered reasonable. There are a lot of people out there who are trying to codify just about everything. And some of them are how to approach the laws of the land. And they get considerably more vague than the air law. I appreciate air law is not trivial. Air law is quite complex. And yes, you run into situations where things aren't covered by the rules. You have to make some.
I think I probably don't have a satisfactory answer for you beyond to say, yes, this is complicated. We can offer techniques and tools that help. And to be honest, it's the same with verification. That I do worry that people assume that when you say we can verify it, that removes any need for thought. And it's easy to verify something that's trivially true. It's easy to verify a thing that's not the thing you really meant you were trying to do. It's easy to verify a whole load of properties and not actually capture the one that genuinely captures what it means for a system to be safe or ethical or whatever. And so I think in this case, it's the same. Some things are just genuinely difficult and you have to approach them mindfully and carefully and do the legwork and do your best. And there are tools and techniques that can help make it easier and help make it more tractable and show you routes forwards. But I don't think any of these excuse anybody from actually thinking, if you see what I mean.
Yeah, no, I see what you mean. And I think, let me pose it another way. Is this, and I appreciate the answer, and I think I tend to agree with you. Is the answer that actually there are times when we should say, this isn't actually practical to code, that actually this isn't something that can be automated, and that actually humans do need to be involved?
At the moment, absolutely yes. There are applications that we should not be handing over to the machines at the current state of the technology, that we should not be considering handing over to machines at the current state of the technology. I don't like to say for definite what will happen 10, 20 years in the future, but at the moment, there are some clear no's where humans should be involved at all times. Well, not necessarily all times. Humans should be involved in some respect, and the humans involved should understand that they are genuinely, their job is not to rubber stamp what the computer says. Their job is to use the computer to help them make decisions, but that the responsibility is theirs and they better check it's the right decision.
Understand. Yeah, no, thanks ever so much. Wonderful presentation. Thank you.
Finally, Jane, if you want to ask your question.
Thanks. I was just going to say it's a really great presentation, and sorry I have to dash off because I have another meeting at 2:30 that I'm already late for. But you were talking about driving examples, and one that occurred to me is in South Africa, when you're driving towards a roundabout, the person who arrives at the roundabout first has right of way. So there's some very interesting ethical decisions there that are slightly more than normal politeness. People wanting to get around the roundabout. So how you would program from an automated driving position, how you negotiate that position where whoever got first, and then are you motivated to drive faster up to the roundabout to make sure you get there first, which is more dangerous for you and potentially other people as well. So it'll be an interesting ethical.
No, I have a PDRA looking at the UK Highway Code at the moment, and he says nearly all the rules in the Highway Code are at the level of we advise you to do this, not that you should do this. And so at the moment, he's coding up agents which will obey all of them or only obey the ones that you absolutely have to obey, and will sacrifice them if it's going to get them somewhere quicker, as it were. I'm not quite sure what he plans to do next. I think there's going to be some simulations and he'll see how many cars crash.
Be interesting.
Yes. But I mean, I think that's sort of part of this answer, that there is a lot of variation and sort of goal optimizing behavior, and a certain amount of kind of very subtle social signals go on in all these situations, which allow these systems mostly to function without massive pileups. But figuring out exactly what that is more complex than simply getting the highway code.
Thank you. So I'm aware of time, but I would still ask a question myself. How do you see the perhaps move forward from verification to synthesis? Because we are discussing about verification. This imagines that the actions of the agent are kind of coded, and we are now verifying the system. Well, what about the agent actually synthesizing online these decisions? Well, what sort of mechanisms could we use for that, or are you aware of any work in this direction?
Well, not in the sort of ethics thing, and I'm actually trying to think how it might work in the ethics situation, in that we have this lack of clarity about what the properties we are trying to prove. So it's like we glue the properties on top of something which is already a synthesis problem, because they're there. The users tell us what their rules are or their utilities are, and we have the decision mechanism. And in a way, that's, you know, a good old-fashioned AI system in a declarative kind of format. You stated the problem and then it figures out the solution. So yeah, it's hard to think how like kind of normal synthesis from a property would work here, because in some sense the property is in conversation with this this set of rules that someone's given you, and those rules are, well, usually implementation, because you've got some kind of logic programming language you've used, so the rules are also the implementation. Of course, you could just have the rules and then you could go away and synthesize some C code.
Yeah. Okay, humans do synthesize our actions, but yeah. Right. Well, thank you again, Louise, for the thought-provoking seminar and answers, and thank you to everyone who attended and asked questions and participated in the discussion. And I'm looking forward to seeing you again at our next seminar in 2 weeks' time.